between individual values versus the means that we were talking about. So here is the problem. National Center for Health Statistics, the US, is according to them, the distribution of the serum cholesterol levels for 20 to 74-year-old males is 211 milligrams per deciliter, and the standard deviation is 46 milligrams per deciliter. This is what the data is. Now I have two questions. What is the probability that the serum cholesterol level of a male, so population is 20 to 74-year-old males only, the serum cholesterol level of a male is more than 230 milligrams per deciliter. The second part of the question is, what is the probability that the average serum cholesterol level of a national sample of 25 males will be more than 230? I have the same population, I am interested in the same value. So notice the difference between the two problems. In one case, I am interested in one individual's cholesterol level. In another case, I am interested in the mean of 25 such individuals. The mean cholesterol of 25 such individuals. That's the difference. One individual versus mean of 25 such individuals. How do I do this? First one, how do I? The assumption is that they are normally distributed. Okay. First one. What do I do? Set score. What do I set score? That's the speed. I like that. Okay. So set score. So what is the set score now? That's it. 230 minus 211 divided by 46. That's my z-score. Okay? That's it. And then I get my P naught more than 230, so 1 minus P naught. Done. In the second case, what do I do? Z-score. Okay, z-score for the second one. It's a sample distribution of means. Previously it was a distribution of the population. Okay. So 25. So the standard error. Okay. So now what do I get? What is my z-score? 230. I'm still interested in the same value. 230 minus 211 divided by 46 divided by square root of 25. 46 divided by 5. 9.2. This is a new distribution, the distribution of the means. So the standard deviation of that distribution is not the standard deviation of this distribution. It's population. So let me just draw that and that's it. So let's first do it in R and then I will draw that and show you the impact of that. Oh, sorry. R. Okay. So here 1 minus P naught 230. The same thing, okay, the other one, the apples P naught 1.8 standard deviations minus 1.8. We got 92.8. And 1 minus P naught, that answer is 33.9, about 34%. 1 in 3 people among those 20 to 74-year-old males will have a serum cholesterol level of more than 230. That's what this is telling me. 1 in 3 people. Now the second one was the sample, and that says 2%. It's nearly impossible to have a sample of 25 such males, their average being more than 230. See the significant difference there? And that's happening. Let's visually look at what's happening here. So let's do this. Now the first one was the population. So So let's do the population with the blue. You'll keep noticing what am I doing. I'm doing the same. Just draw the axis. Wow. Okay, and over here. I need to draw this also. Okay, so what is this number here? This is 211. Okay, this is my population distribution. And 46 was the standard deviation. So I want to understand the limits. Where does this end? So 46, one standard deviation means 3 standard deviations on 138. 211 plus 138. So somewhere here at the 99.7 limits is 349. And someone do 211 minus 138. So 62, 73. 138. 138, yeah. Not right? Okay, right. So this is what my population distribution looks like. Serum cholesterol level 73 to 349 is ranging. 68% of the things will be within plus minus 140, so plus minus 46. So this is 1 sigma. Okay, 1 sigma. Okay, so I am interested in 230. 230. So this 1 sigma is 46 means 257. I am interested in 230. 230 is somewhere here, isn't it? 230. So this is the area I was looking at. 1/3. Agreed? Okay. Now let's go to the sample. The sample distribution of the means. Maybe I should go and write next to that, or let's just keep it there. Okay, right there. And now my sample distribution of the means. Okay, not as now, but actually I should have gone there. So this is 211. Population mean, sample distribution of means will be the same. Now, the standard deviation of this is 9.2. 46 divided by square root of 25. 5. So 9.2 or something. Okay. So 3 standard deviations is 27. So 238 is somewhere here. 238. And 27 subtract from here. 11 and 16, 184 is somewhere here. About 184. And I am interested in 230, which is right there. 230. So this area is 2%. See. So what we really are saying is that when you take a random sample, see individuals, there are a lot of individuals with a height more than 230. But if I am taking a random sample from this distribution, I will take some people from here, some people from here. I will have all kinds of things, no? I won't have all the people picked in a random sampling from this region only. If 25 people end up from that region, then it's not a random sample. And if I take a random sample like that, getting their average to be more than 230 is not right. That's not as right. That's what the sample distribution is telling. Fine. Sample distribution. Now we will see how this standard error and all those things that got introduced from the sample distribution, how does that come into play into our actual inferential methods, the inferences that we make about populations. How do we do that? The first one we will talk about is confidence intervals, and then the next one, hypothesis testing. They are one and the same thing. I will just tell you, the way of looking at the problem is slightly different, but they do exactly the same thing. It's up to you whether you want to use the confidence interval method of doing it or hypothesis testing. Both are the same. Linear regression is nothing but a hypothesis testing that we will be doing. So sometimes it's more convenient to use hypothesis testing, sometimes it's convenient to use confidence intervals, but there are hardcore statisticians who will swear by confidence intervals only. I like them only, I don't want to do this. There are people who will say, I want to do only this, I don't want to care about this. So, but both of them do the same thing. Okay. So we will talk about them in great depth because this is where all the inferences come in. Confidence levels and confidence intervals. Having said that, I'm not going to be teaching you anything new. Only two terms are going to be introduced. I will tell you what I have already told you in a new package. Okay, so we see these all the time. Exit polls, see photo finish. This was last year Bihar election, I guess, or 2 years back, after the assembly, after the general elections. And you see how they say India today predicts 120 seats for BJP plus, 117 here, and various organizations are predicting various things. And these people are very nice, the newspaper people. What they have done is nicely to have this shouting headline there, screaming headline. They actually average all of these to get 118, average all of these to get 118, and then they say there is a photo finish. There could be photo finish just by showing that part itself, but they do all that. If you read the article, if you really care for this, what it says is, this India Today poll shows that they predict 113 to 127 seats for the NDA and 111 to 123 seats for the JDU alliance. So what they have mentioned here is the midpoint of that range they have got. 120 plus minus 7, 117 plus minus 6. That's what they really are saying. In the table they have not mentioned that, but that's what they are doing. And I think another study also has that breakup given. These people have not given that, or the newspaper has not reported that. So 112 to 132 and 101 to this thing. You see, if they had not given this part here, it might look that they are saying JDU is fairly ahead of BJP plus. But if the moment you put that plus minus 110, this could be 121, this could be 10, 112. Thing could have been switched also. There is a range being mentioned. What is that range? How do we calculate that? What does that mean? That's what I want to understand. Okay. We have seen that with the apple example. Is it plus? I have a sample apples, and I am saying is the population mean with it plus minus 12. That is like something very similar. That's all I am talking about. Okay. So I just wanted to plot these and see is there a photo finish, and I plotted it for only those two because they have given the ranges 120 plus minus 7, 117, okay, 117 plus minus 6, this is 111 plus minus 10, 122 plus minus 10, that's 10. And now you see there is a significant overlap between them. That does state that it's a photo finish. It's a different matter that results are completely off of any of these people. None of them predicted anything correctly. But that shows a photo finish kind of a thing. Anybody could do it. Fair. But the way they present is not optimum. That's not the best way. So there is this uncertainty, this plus minus, the moment they are talking about plus minus, there is an uncertainty because you are taking a sample and you are talking about a population. There is that error we have talked about. There is that uncertainty. We call it error, I am now calling it uncertainty. It's the same thing. So that needs to be quantified. And these people in the general elections, NDA actually won 336. What does this convey to you? As non-statisticians, when I read this, I say, okay, News 24 Chanakya is saying 340 plus minus 14, so BJP combined will win anything between 326 to 354, and yeah, they were 336. But that's not entirely correct. That's not the way we should be reading that. Now that we also know the empirical rule, 68, 95, 99.7. Okay, so there is that probability associated with that. How much of data will be, how much of that will contain the population mean? So we will talk about that. These other guys, of course, they say, well, 249, there will be 274. There is no error. Too confident. Very confident. Okay, so we have seen this just now. Okay, and what we have seen is that 68% of the times the population mean will be within plus minus 12, or in the apples, one standard deviation of the mean, and 95%, 99.7, we know that. Okay, so what that really means here, that 95%, 99%, that is actually the confidence level. We have been seeing 95 also. What is that? That's the amount of data under the curve, area under the curve. How much of total data is contained within that range. That range is called confidence interval. The amount of data contained in that is called confidence level. Why do I need to again talk about this? Okay. So let me just show you what that really means is. I'll do this demo again in Excel. What the confidence level and confidence interval really means. It's the same 95%, same range. X-axis value and the area under the curve. Nothing different from that. But what it means is, okay. So here again, I generated data with a mean of, so 5,000 data points again. 5,000 data points I generated here. This just goes on, 5,000 data points all the way. So there you go. And I gave, when I was generating the data, I said the mean of the data should be 120 and the standard deviation should be 25. With that, I generated this random data. Now, I am taking samples. I made 100 samples, 5,000 data points, 100 samples, each sample 50 data points. So I took 50 data points, the first 50, and I called it sample number 1. So this is all sample number 1 up to 50, and then after 50, sample number 2. So I calculated the mean of the first 50 data points, that is 116.23. Mean of the next 50 data points, 117.58. Like that, mean of those 100 samples. So 100 means I have. Okay, clear what I am doing as of now? And now, I am saying 100, so mean plus minus 2 standard errors. I am interested in 95% of the data being contained. So I am saying plus minus 2 standard errors. Okay. 2 standard errors. How do I get the standard error? Plus minus 2. Actually, if I just use the all those things, it's not exactly 2, it's actually 1.96. The correct z-score value is 1.96. They round it off to 2, which is okay, just for your understanding, because from now on we might start using 1.96. Don't think it's a new thing. 2 is just the approximate number. Okay, 1.96. So, or plus minus 2. This mean minus 2 times the standard error. 2 times the standard error. How do I get the standard error? Standard deviation of the population is known. 25 divided by square root of the sample size 50. So that's what I have done. I get a value. Likewise, I do plus 2 standard errors. That sample mean minus 2 standard errors plus 2 standard errors. Sample plus minus this. That's what I have done for all the 100 samples. And that's what I plotted here. So first sample had a mean of 116 point something, we saw that, plus minus 2 standard errors. Standard error is the same. Population standard deviation 25 divided by square root of 50. So plus minus 2. That range is constant. And I am doing that. I have plotted all of this. I know the population mean is 120 because that is what I generated data with. Now I want to count the number of samples that contain the population mean within that range. Is 120 covered in this range? 116 plus minus 2 standard errors, the first sample. 120 is there. There? Right. So if I use that sample to make inference about the population, I will say the population will be somewhere between this and this. And I will be right. Isn't it? 120 is there in the range. Now, this one, is it contained? 120 is not contained. If I had this sample, I would make an inference that the population mean will be in this range and I will be wrong. I will be wrong. How many times will I be wrong? Okay, here I am wrong. Here I am wrong. Here I am off. Maybe even this one. This one is off slightly. Some of them, this one is slightly off. So I counted them. 94 of these 100 intervals contain the population mean within their ranges. That's what I'm saying is my confidence. I'm saying 95% confidence is 95 is an approximated thing. A real word, nothing will ever be perfectly there. Next time I do the same sample thing, I might get 92. But it will not be 50. Guaranteed it will not be 50. So that's what my confidence interval is really telling me. That 90, when I say 95% confidence level, then I'm saying 95% of the samples will contain the population mean within that range that I'm specifying. 5% of them have been wrong. What can I do? Okay. If you want to be 100% of the time correct, you will get the data from the entire population. Cost. Okay. So just to show this again in a different format. So this is my data. If my first sample is here, obviously population mean is within plus minus 2 standard errors. If my sample mean is here, any